Okay, can you share, Doctor?
I think, yeah, let me see. Let me see. Just a second. Yeah. Hmm. Just a second.
Right, it's okay.
Yeah, we'll just. So can you see my screen? No?
Not yet.
Yeah, let me try again. Hmm.
Doesn't work?
I'm trying again. For some reason, it's not letting me share.
Ah,
I don't
but
know why.
okay. I have allow another participant to share, but I'm not sure why. Or you want to or you want to share with me your slide in WhatsApp, and I can share maybe.
So just a second, I'm just going to check again. It
All
might
right.
be security and preference. Just a second, sorry.
Okay, it's
It
okay.
might be,
It's okay, Doctor.
I'm
Take
thinking it
time.
might be because I'm using a university laptop, so it might be security. um, Preferences. So maybe if it's not working, I might just send you the slides
Yeah, please.
and then you share.
Yeah.
It's
Okay.
not ideal, but yeah.
But
But
don't have your number. You can
no, I'm
share.
going to send to you by email.
Oh, all right. Okay.
So if you just, oh, I can see you're joining on the Maslina's email.
Yes, yes.
So
I
should I
use her
send to
account.
Maslina's email?
Okay, you can share with her, but I just worry she not look on her laptop. But okay, I call her. You can share
No,
with
no,
her.
no.
Uh-huh.
If you just give me your email, I can send to you.
Okay. I in message, I type my email.
Yes, please. Sorry about that.
That's
That's
okay.
that's quite strange. It's very strange.
Okay, you got it? Dr. Akilu, in message?
Just a second. I'm just going to check in chat, right? Did you put it in chat?
Yeah, in chat.
No, it has not come.
Oh.
Or let me do this. I'm going to send you my email, and if you just send me an email, okay, it has come now. It has come now.
I typed to
Yeah, your
you,
email has come now. Don't worry.
Elma 82
Yes, it has
8207
come
at
now.
UiTM.
All right.
Yeah, I'm just sending to you now.
Okay.
So that's text on. So I have sent to you.
All right, I refresh my.
I've sent you the slides now.
Okay. Let me.
Because we don't use Zoom
I
anymore.
see.
We use Teams.
Okay,
So I don't know if that
I
has
saw your
anything to do with
email.
it. Yeah.
Okay, wait, I download first. Okay.
Just a second, I'll leave and join again.
Okay. Everyone have see the screen?
Yes.
All right.
Yeah, Doctor.
Yes, doctor.
Now we
Like
see
in
the
slideshow or not?
No.
No.
Not slideshow. Okay, this one slideshow, right? Or not?
Not slideshow.
Yes, but not not
The
not
full-
in a full screen. Not full screen.
In full
Not full
screen?
screen.
How I
Yes.
want, because with me it's slideshow already. Dr. Akilu left ya?
Ah,
Yeah. Merajuk.
Maju. Macam mana I nak fullkan screen lah? But
Bawah-bawah tu tak boleh.
dekat I already slideshow.
oh, dia kena switch screen kan.
Sekarang macam screen yang
Screen share.
dekat
Dia
screen yang
terbalik.
sepatutnya dekat laptop doktor.
Yang this one? Sama.
Ah, okay.
Yeah,
Right.
okay.
ini
So,
betul dah.
can you stop sharing? Let me see if I can share now.
Oh, okay.
If I can't, I just want to try for the last time.
Alright.
You just do it. Yeah.
Yeah, how I want to stop.
I've tried to check the security.
Okay.
If you just stop
I think you
sharing.
can concurrent share. Which one?
If you, let me see if, so did you say concurrent share?
Yes, already setting for the concurrent share.
Okay, okay.
Well, because
So that's,
I don't know where to stop because I also not familiar with the Zoom actually.
yeah, because Zoom for me is not very, so what can you, so let me see. So can you see my screen sharing now?
Yes.
Okay.
Okay,
So
but
that's,
it's not still not in slideshow.
yeah, I know. I
alright.
just want to make sure. Yeah.
Okay.
It is in slideshow now,
Yeah.
isn't it?
Yeah.
Yeah. Okay, yeah, we got there in the end. So sorry.
Okay.
And good afternoon again, everyone. I am Akilu. I'm a reader in reliability and maintenance engineering. I'm also the head of education for the School of Engineering at the University of Manchester. Yeah, my background is, my fundamental background was in vibration of rotating machines, but my master's was in reliability, and I worked a lot on reliability in the industry before joining the university as an academic. Now, today I'll be discussing a reliability-based approach to learning from success and failure in design with some examples. I'm using generic examples. So for example, some of the examples I'll be using are generic, but there are components that are used across a range of industries and sectors, including construction. Please feel free to stop me at any point if you feel I'm moving too fast. The motivation for my topic, successes and failures, is that there's as much to learn from success as failures. Of course, one or the other leaves more mark on us. Most unfortunately, when we succeed, we tend to forget quickly because it's a positive. But when we fail, we tend to remember for much longer. So people emphasize more on failures as opposed to success, but there are equal lessons to learn from both premises. So the learning outcomes for today would be to understand the fundamental principles and features of learning from failures and successes, understand the fundamental principles of using reliability-based techniques. In this case, we'll be looking at qualitative and quantitative risk assessment tools. I've picked some of the very prominent ones for design, quantification, and failure analysis. Just before we get on, I just have a few questions here. You don't need to post your answers, but just look through these 8 questions and try to match. The answers are at the bottom right-hand corner. Okay, so each question has an answer. Some questions have more than one answer. Okay, so if you think question 1, the answer to question 1 is A, just write A, just write Q1A by the side on a piece of paper with you, So, and at the end of the class, I'll show you what my answers are, and then you can check them against yours at your convenient time, okay? So I'll just give 2 minutes for that. 'Okay, are we all done? We should be finished in the next 30 seconds. Don't think it too much. Ten seconds. Okay, let's move on. You'd see the responses at the end of the lecture. Now, a brief introduction to learning from safety experiences. Now, we do know that accidents do cost a lot in terms of sometimes, depending on how severe they are, they could lead to injuries, they could lead to loss of life. They often lead to downtime, which costs organizations money. And in some cases, depending on the severity, if it's been proven that you've violated some regulations, it could lead to litigations and fines, and sometimes even shutdown of businesses, which are very, very expensive, okay? Detailed and effective accidents investigations often give us the opportunity to understand what we've done wrong or to anticipate what might go wrong in design. So you could use accident investigation techniques to appraise an existing design, or as well as you can use data from similar designs from elsewhere to appraise and to kind of predict what might go wrong in a new design. So it can be used as a proactive as well as a preventive approach, okay? In conducting a detailed and representative accident or failure analysis or design quantification or design risk analysis or design risk assessment, all aspects of the engineering and management must come together. So you need people, you need to understand the equipment, what I call the 5 M's. So you put people, the budget, which is money, the materials, the methods, and so on and so forth. You need to assess in regard to all these 5 M's. There are some approaches. So, for example, some organizations do root cause analysis in a haphazard manner, either using some software. Yes, they could work, but a fundamental success factor to those kind of approaches is you must have an extremely experienced team that is very familiar with that system. This is not always available. Sometimes you might have auditors that are not part of your organizations, which is why the use of systematic approaches, such as those that we'll be discussing today, help. And even if you have an experienced team, using a systematic approach helps people to trace back the steps and the processes they've gone through to arrive at any decisions they've taken, so that people coming to do the same activity after them or to check the validity of what they've done can just trace back those steps, okay? The design stages of engineering processes offer a lot of information that we can use to improve our chances of success. Now, over the years, there's been a lot of tools for investigating failures or for appraising designs and so on and so forth, but failures still occur. So we need to ask ourselves, why are we not learning from previous experiences? Buildings are still collapsing. People are still being struck by cranes. Cranes are still collapsing on construction sites. Why are we not learning? Now, the flip side to that is we also train our people a lot. Organizations invest a lot in training. So in the situation whereby you've trained someone, why are they unlearning the knowledge they've acquired? Okay, so these are some of the things we'll try to look at today. So I've just put together a generic kind of flow chart here. Some of the most fundamental reasons why designs fail, okay? You can link any kind of failure to one or more of these categories. So fundamentally, they either fail due to inherent weaknesses, which could come from either using a cheap option or poorly executing the design. So the design idea might be very good, but the execution of that design might be poor. Using substandard material. So I'd be very careful here. You can see some people might ask, what is the difference between cheap option and substandard material? Standard is not always defined by cost or by how expensive something is. Some very expensive items might be poor in standard. Sometimes some cheap options, just because they're just coming into the market newly, might be of very good standard. So that's why I've tried to differentiate that. And then, of course, it could be the manufacturing process. Then, if we move on, so this is all around the design. Sometimes the design is fine, the equipment is well manufactured, but they still fail. Why? Because we're using them in the wrong way. Either we're using them above their safe working limit, we're exceeding the tolerances specified by the original equipment manufacturer, and so on and so forth. That's what we call victimization. Now, victimization could come either functionally, whereby you have installed poorly. So a good equipment, if you install poorly and use the wrong tolerance and fit, it would fail. You've commissioned wrongly. If the manufacturer said, commission over 6 months and increase load by 10% every week, but because you don't want to wait 6 months, you're in a hurry to start making money, you commission over 1 month, and you're not allowing equipment to go through their entire cycle of failure. So that could be one. Maloperation, if they say run at 100 revolutions per minute, and you're running at 150 revolutions per minute because you want to produce more. Change of intent, if a bearing is made for the non-drive end and you're putting it at the drive end, you've changed the intention of the manufacturer. And then if you're making modifications that did not go through a proper change management process, okay, then physically, and this is classified into two, either due to deterioration during storage in the supplier store before it even gets to your site, or within your store, within your company, if they're not properly protected from rust or from corrosion before you put them into service, that is physical under deterioration. If you've used them for too long, so if the longer you use equipment, the more they go through what we call the bathtub curve. After a safe working period, they start to wear out and deteriorate. You need to understand that at that point, you need to take them out of service, decommission them or replace them or derate them. So if you're going to keep them in service, you need to make a decision. Okay, this is made to run at 100 miles an hour, but because of its age, we need to drop the amount of load on it. It's just like we people, when we're in our teens and in our youthful age, we can do a lot of activities. The older we get, we need to reduce our efficiency or the amount of load we're putting on ourselves. Not properly maintained, if maintenance practices are poor, that could also speed up the wear rate and deterioration. Or maybe you're not inspecting or you're not protecting them. So, and then of course, damage could happen during transportation, storage, installation, commissioning, operation, and maintenance. So you can fit most or majority of the causes of failure into one or more of these items. Now, let's not forget, we've all been talking about equipment, but associated with each of these components are the people that operate the equipment, the people that manufacture them, the people that inspect them, the people that maintain them. No matter how well designed a component is, if they're not being handled by the right people with the right skill set, according to the right standard operating procedures, those things will fail, okay? So here we're going to look at three main techniques, but my emphasis will be on what we call fault tree analysis and event tree analysis. So fault tree analysis is a diagrammatic representation of causes of a failure. It mainly combines what we call the AND. It will have three main parts. You have the gates, you have the intermediate events, and then you have the basic events. There are two main types of gates, the AND gate and the OR gates. AND gates is when things are happening in parallel. So two events must happen concurrently for that failure to happen. Okay, so a more resilient system will have parallel. Okay, OR gate is either one of the inputs to that gate needs to happen. If any one of the inputs happens, then the top event or the failure occurs. Is this clear? So it's like series system and parallel system. If you have a series system, if any component within that chain breaks, then the whole system fails. If you have a parallel system, it means two things that are doing similar function, which means if you lose one, you can still have the other. So for example, if your house is receiving power from the grid and from a generator, you have a standby generator that goes on as soon as you lose grid power. That is a parallel system. You would represent such with an AND gate, okay? It's one of the most commonly used engineering design quantification technique. This originated from the oil and gas, the aviation, the nuclear, the high risk, they call them high reliability organizations, where the cost of failure is very, very severe. You know, like an aircraft, if an aircraft crashes, you're looking at hundreds of loss of life. If there is a loss of nuclear containment, the implication will be massive. So they do these things. And it's based on deductive logic. You keep coming, if this happens, then what happens next? If this happens, then what happens next? Okay? Here are some simple guidelines to fault tree analysis. So obviously there are no miracles. So if the normal functioning of an engineering design propagates a fault sequence, then it is assumed that the design functions normally. Let me give you an example. You're all from the construction space. If you go on a construction site, when you're mixing concrete and you want to make a concrete slab, there is what we call the agitator. Okay, maybe you've seen it if you've not worked on a construction site. They put that agitator inside the concrete mix, and they put on, the machine keeps vibrating. What that vibration is doing is to move away the moisture, right? Isn't it? Now, by design, that equipment is made to vibrate. It functions based on vibration. So you cannot classify its vibration as a fault. That's what that first point means. Is that clear to everyone? So if an equipment is designed in a way, because under normal circumstances, if you're looking at rotating machines, you say vibration is a fault. But some equipments are designed to vibrate. That's the way they achieve what they're meant for. The second point is you need to complete the gate. You need to, for each gate you put, you need to define all the inputs to that gate before you move to another gate or another event. And lastly, you cannot connect two gates to each other. There has to be an input to a gate before another gate. There is no gate-to-gate connection. Okay? Now, let's look at a practical example here. This is a valve on the right, and valves are used in pressure systems. They're used in hydraulic systems, cranes, and everywhere. You know, I'm sure you've come in contact with one type of valve or another. There's non-return valve, there's pressure relief valve. There's so many types of valves, okay? So let's look at this case. AYK is a manufacturing giant of industrial safety valves to several sectors, including those within construction and built environment. Recently, AYK's valves have been associated with several industrial fires due to loss of containment of flammable gases, okay? Now, an industrial tribunal has ordered that a detailed investigation of the root causes of recent incidents be conducted. So for this investigation, we're deciding to use fault-free, event-free, reliability-based tools. Let's see how that works, okay? It's just an illustration. So remember, in the question, it says loss of containment of flammable gases. So that is the incident you're trying to investigate. So here you have loss of containment of flammable gases. Remember what we said? For each event, you need a gate. In this case, now remember, for this case, they have information about the sequence of events. So they're using this fault tree in this case as an investigative tool, okay? They're using it as an investigative tool, not as a proactive tool. So they're using it to investigate a failure. So loss of containment is the investigated event, and that forms your top event. TE is your top event. Then you come down to all. Now, based on the information they have, they know it could be due to overpressure, due to corrosion, or due to dropped object impact. Okay, so it was dropped, and then that caused an expansion of pressure, and the flammable gas was released, or it was overpressure. Then you pick each class and break them down. So this is intermediate event 1. Remember, we said TE is top event, IE is intermediate event 1, intermediate event 2, intermediate event 3. Can you see? On the intermediate event, then we have another gate. This gate, this is the AND gate. The one that looks like a house is the AND gate. And this is the OR gate that has a curve at the top and the curve at the bottom. This OR gate represents series. What this means is either overpressure or corrosion or dropped object impact can lead to this event. Any one of these 3 can lead to this event. If any one of these 3 happens, this will happen. So if there is corrosion, you will have loss of containment. If there is overpressure, you would have loss of containment. If you have dropped object impact, you would have loss of containment also. But for the AND gate, these 2 must happen together for you to have overpressure. So 1, there must be wrong design, and there must be high pressure trip system failure. Because if your design is wrong and your trip system works, then you will not have overpressure. Because even if your design is wrong, once the pressure begins to rise, this trip system will cut off the system. So there will not be overpressure. So these 2 must happen simultaneously for this to happen. And that's how you keep going until you get to this oval shape or circle shape. Once you get to this stage, you have come to the end of that branch. This is referred to as basic events. So basic events are your root causes. Is that clear to everyone? Okay? If you have a question, please ask. And then you move on to the next intermediate event and develop it further. PRV is pressure relief valve stock. It's stuck, so it was stuck up in an open position and it didn't allow pressure to go out. So that caused overpressure. And why is that happening? There was dust in the spring, which made it lose its compressibility. There was a blockage of the nozzle, which means excess air could not be released. Blowdown ring was 1, okay? So that was not allowing the blowdown activity to happen. So, and that's how you keep going down. You see here, there is inaccurate setting of the high pressure trip system, either due to an unskilled technician or loss of calibration. So you can see there is people, there is process, there is design, everything comes in here. CBM is condition-based maintenance, so routine inspection, checks, and repairs, okay? And for the dropped object, lifting over an operating plant. So if you're lifting a pressurized vessel over an operating plant and it drops, that would cause a hazard, okay? That would burst and lead to loss of containment. Or wrong lifting equipment. If you're using the wrong lifting equipment, for example, the equipment you're using is less than the safe working load. So it's lifting over its capacity. Or maybe the slings that you connected to the object you're lifting are worn and they snapped midway. Okay, so this is how to keep drilling down. Now, as good as fault tree analysis is, trust me, this is one of the simplest of examples. In real life, practical fault trees could be tens of pages long with a lot of inputs for real complex systems. So sometimes it becomes a bit overwhelming to analyze when you have so many inputs and a very busy diagram. Even this in itself looks busy, so you can talk about having tens of pages. So that is why sometimes we convert it to reliability block diagram so that everything comes out in a simplified form of blocks and you can outrightly see what is critical and what is less critical. So this is an example. This is the equivalent reliability block diagram of this fault tree analysis. And you can see here, I'll give you just a brief example. You see B1 and B2. What would you say is the relationship between B1 and B2 here? Can anyone tell me? What kind of relationship is this? Let me know if I've been speaking to myself.
Parallel.
What, sorry?
It's in parallel.
Yes. So this is parallel. What kind of gate would have connected these two in the fault tree?
N.
Excellent. So if we go back here, you can see B1 and B2 are connected by an AND gate, and that's why they're in parallel. And B3, B4, B5, B6, these are in series. Excellent. And that means they were connected by an OR gate. So let's look. You can see B3, B4, B5, B6, B7. OR gates, OR gates, OR gates. Is that clear? Is that clear to everyone?
Yes.
Yes.
Yes,
Yes,
Doctor.
doctor.
Doctor, may I
Excellent.
ask a question?
Yes, please.
The previous slides.
Yeah.
So how do we know that the cause has reached the roots? Example, lack of coating, we just end in that level, while the post CBM, we study more further.
So there is a thumb rule, but there is also reality. The thumb rule is usually you don't go more than 5 layers. Okay, but that is just a thumb rule. It's also, but how far you go is a function of the complexity and the criticality of your system. Sometimes you might want to go further down because, for example, if you're in the nuclear industry, you want to go to as far as possible because the consequences of a failure could be dire, okay? For example, in nuclear industries, you might have up to 5 sets of redundancy just because they cannot accommodate any failure. That's one. 2, what I usually say to people is your base event should be the level in which you can take a definitive action. So if we look here, wrong design. If you had stopped at wrong design, for example, I don't think you have reached the root cause, because if you say wrong design, why do you have a wrong design? It could be due to 100 different reasons. But once you've reached here and say you do not have a quality assurance and a quality control process, those are actions you can implement. So we need to implement quality assurance, we need to implement quality control, and you can test the effectiveness of those two, okay? For example, for corrosion, lack of coating, there is no need for you to go beyond that. You just need to apply coating, right, to prevent corrosion. That is well established. Here, inaccurate pressure setting, you've come down to your technician is not skilled. So the decision is on you. Do you want to fire the technician or do you want to train the technician? Those are actions you can take. Those are action points. Loss of calibration, you just need to calibrate. You know, so once you get to a point where you can take a definitive action, not when you start asking yourself, once you're in doubt whether one action will eliminate the top event, then you have not reached the root cause. That is another thing you need to ask yourself. Once you're in doubt whether an action that comes to your mind cannot eliminate that failure mode, then you have not reached the root cause. Is that clear?
Clear, Doctor. Thank you.
Thank you. So now you can see that this is a simpler diagram to look at, okay? You can see from here, okay, we need two things to happen here, but this one, any one of these can lead to the failure. So your series, so if I ask you a question, in this diagram, which part would you say is the most critical? Which part would you focus your most attention on? Let's assume each of these represents stages within your construction operation. Which stage would you focus your most effort?
The B3 to B7 stage.
Why?
Because they are in series. Because anyone will give the root cause.
Okay. I have a question for you. If B5 fails, do you think this whole IE1 will fail?
No.
No.
No, because you have B1 and B2 in parallel to B3 to B7. So in my opinion, IE3 is your most critical, this part. Do you understand why? Because if you lose B12 or B1 or B11 or B13, IE3 fails. And if IE3 fails, that means the whole of your TE has happened, because without IE3, this cannot happen. This cannot progress also. Is that clear?
Okay.
Yes.
Yes, good. So we finished with fault tree analysis. Fault tree is most often used as a preventive tool. You use it to investigate in design. In a new design, you use fault tree on the preventive side. There is also something, so let's assume we know in reality, no matter how much you prepare, some things still go wrong, right? So let's assume you do all your preventive measures with your fault tree analysis and a failure still happens. Then you need to start thinking of how to react. So you need to start thinking of how to deal with the consequence. And that is what you use the event tree for. So event tree shows the likely outcomes that may result from an accident, which is often referred to as initiating event, by using an inductive reasoning. Remember, fault tree is deductive, event tree is inductive. So ETA examines the adequacy of existing safety barriers. So you're thinking about so from your fault tree, you've identified some barriers to prevent those failure modes from happening. Your event tree checks whether those barriers have done their job and what will be the consequence if they don't do their job. So you're thinking about the consequence. For example, if you build a house and you put fire protection devices like sprinklers, like stairs, escape stairs, emergency exit, you need to now ask yourself, you use the inventory to say, what if the sprinkler system fails? What will happen? Will the fire alarm go off? What if the fire alarm doesn't go off? How will people locate the emergency exit? What if they locate the emergency exit? How many people can the emergency exit stairways take to prevent injuries and to get people as quickly as possible away from the fire? You know, so this is how it works. And then event tree can be used to identify potential or unwanted scenarios. Let's look at some further steps. So you need to determine an unwanted event, which is often referred to as the initiating event. Determine the existing barriers to deal with such an event. Then you construct your event tree analysis. Now, you can use it either as qualitative or as quantitative. If you have the probabilities of failure data and the frequency of failure, you can use it, you can plug those figures into each of the parts and use it to predict the probability of each of those events happening. Okay, that is the quantitative risk assessment approach of it, or quantitative risk analysis approach of it. If you just want to use it to have an idea, for example, you want to use it to train a team, you want to use it to just see what could go wrong in a qualitative sense, then that could be qualitative risk assessment. If you're using it for quantitative, then you need to include steps 5 and 6. If you're using it for just qualitative, then you just move on to step 7. So let's look at an example. So let's assume from the fault tree, we were looking at loss of containment. So let's assume that loss of containment has happened. The barriers we put in our fault tree did not work. Then we had the fire, okay? What you do in event tree, you had the fire, which is the initiating event, that's the fire. So first thing you need to ask yourself, did the fire start? If the answer is false, then no fire, okay? If the answer is true that a fire started, then you need to look at what protective measures do you have for fire. So you have a sprinkler system, okay? Did your sprinkler system fail to do its function? If it's false, that means your sprinkler system did not fail. But if your sprinkler system failed to do its job, that means it's true that the sprinkler system failed. If the sprinkler system did not fail, then you have a false. That means, remember, of course, you're on the true path for start of fire, which means there is already a fire, but the sprinkler system did not fail to do its job. So that means you have a fire, but it was controlled because the sprinkler system worked. If the sprinkler system, however, so here you have the third batch, which is you have the sprinkler system, you have the fire alarm, and then you have the outcome. So sprinkler system did not fail to do its job, but there was a fire, but the alarm, did the alarm fail to do its job? Yes, the alarm system failed to do its job. Okay? Do you understand? The alarm system failed to do its job. So you had a fire, and that fire was not controlled. And the fire was controlled because your sprinkler system did not fail to do its job, but people were not alerted. Is that clear? Now, on the true path, the sprinkler system, there is already a fire. The sprinkler system has failed to do its job, but the alarm functioned. Okay? So there was a fire. The fire was not controlled because there was no sprinkler, but at least people were informed by the alarm. Now, the worst scenario is there was a fire, the sprinkler system failed, which means there was no control for the fire, and the alarm system did not work also, which means people were not informed. So you had an uncontrolled fire without alarm. Does this make sense to you? And the way this is arranged, the lowest outcome is the most favorable, and the highest outcome is the most severe. So if you had data around the frequency of failures or probability of failure, this would have the highest probability and this would have the least. Is this clear?
Yes, doctor.
Excellent. Now, in reality, we need both to work together, isn't it? We need preventive and we need reactive. So we need preventive so that if anything goes wrong, we know how to react. And that is why they combine fault tree and event tree into what we call a bow tie analysis. So bow tie is basically on your left-hand side is the preventive or the root cause, which is your fault tree. And on the right-hand side is your reactive or your consequences, which is the event tree. Combining them together, you get something like the shape of a bow tie. So you can see here on the left-hand side, you're dealing with causes and root causes, which is associated with fault tree. These are your barriers. Sometimes you need to also rank your barriers. Once you know your most critical barrier, then you need to think of escalation events. So for example, let's say driving. I know we all drive. Let's say accident. The major cause of accident is because drivers do not wear seatbelt. Now, let's assume you put a rule, you must wear seatbelt. But let's assume even with that rule, people are still not obeying. So you need to think of an escalation factor related to seatbelt. Maybe you can say we need to train people on how to use seatbelt, or we might want to go with the stick approach, whereby we say if you're caught not wearing your seatbelt, you lose points on your license, or we stop you from driving. That is what we call the escalation factor. So you would have barriers for your causes on the left, and you would also have barriers for your controls, for your consequences on the right. Let's look at the two examples we've looked at for the fault tree and the event tree and combine them together. So you remember the fault tree, okay? And this is the event tree. And if you do that, you have your bow tie, okay? And then now you can extract all the information you have. So you see on the left, you have preventive for the causes, and on the right, you have reactive for the consequences. How do you react to a consequence? And this is what you have. So this figure is what I've simplified into here. So you see we have, remember from your intermediate events, you have overpressure, corrosion, and dropped object, okay? And that's what we have here, overpressure, corrosion, and dropped object. And the outcome here, fire, explosion. So you can see your control for preventive, and your control for reactive. In here is the fire, which is the intermediate event, okay? Then you can see CP1, designed to relevant standard, routine PRV, pressure relief valve calibration, staff training, apply HC grade corrosion, coating. Remember we talked about corrosion. Optimize your condition-based interval to weekly. Maybe the interval was too long, and you know, so on and so forth. And then for the explosion, control for reactive, we said gas detection and emergency shutdown, ventilation to disperse gas and reduce concentration of gas so that people do not inhale the gas. Hazard area classification, so you let people know this is the most hazardous area of your site. This is the least hazard. You need to move if there's a problem from this area to this area. Sprinklers and fire alarms functional testing routinely. Firefighting systems, hydrant extinguishers, so that in case fire service comes, there has to be access to hydrants and so on and so forth. Okay? And with that, we've come to the end of my talk today. Sorry, I rushed a bit. I wanted us to finish everything within the time allocated. So these are the answers to the brain teaser questions you had at the start. And I believe this is being recorded, so it will be shared with you eventually. And with that, I've come to the end of my lecture for today. We looked at fundamental principles and features of learning from failures and success using reliability-based tools. We looked at the impact of individual and organizational barriers to learning from the past. We generally talked about some very prolific reliability-based engineering tools for learning from the past. Thank you very much for your time, and I'm happy to take a few questions if you do have any. Sorry, it's incredibly busy for us at this time of the year. Our students just finished exams, so we're having so many exam boards here and there. Yes, so yeah, thank you very much for your time and for attending the lecture.
Okay, thank you, Dr. Akilu. We here also Dr. Mike. Okay. Okay, before we start with Dr. Mike, any question with for Dr. Akilu? I think I can open 1 or 2 questions to ask Dr. Akilu before we start another session with Dr. Mike.
Yeah.
Yes, Anderson, please.
Doctor, for the different analysis that you presented, are we going to do it per event?
Yeah. So for fault trees, you do them per failure mode. So yes, you need to do it per failure mode. And of course, the level of detail you do to each will vary. You know, very critical failure mode. So you first do your criticality analysis, you know your failure modes, you know which one are most critical and which one have the highest impact or consequence. Then you focus on those and use this approach. This approach is usually dedicated to very, very critical failure modes. You can't use it for anything. For example, if somebody slips or trip, you know, some very minor things that you can address with common sense, you don't need to go through this, this process. But those very dynamic and complex problems that involve a whole lot of team, there is a lot of dependence between different actions. Yes, this is what this is most suited for.
Thank you, Doctor.
Yeah, you're welcome.
Any other question? I think we can open another one question. Is everyone okay? All right. Okay. I think thank you very much, Dr. Akilu, for your sharing all your knowledge. I'm sorry for the technical issues.
No worries.
Okay.
No,
Okay,
it wasn't
before-
your problem. It
All
was
right.
from my IT.
It's okay. Okay. I
Yeah.
think before we end with Dr. Akilu, and I think we can snap a picture first.
Yeah, that's fine. Yeah.
Everyone, include the mic, please. Okay, ready? 1, 2, 3. All right. Okay. All right. Thank you very much, Dr. Akilu.
Thank you.
All right.
Thank you.
Okay,
All
see
right.
you.
Bye-bye.
Doctor.
Bye. Yeah, bye.
Okay, thank you, Doctor.
Thank you,
Yeah, you're
Doctor.
welcome. Thank you very much.
Doctor.
Yeah, bye-bye.
Mana ke, Doktor? All right. Okay, hi. Good afternoon, Dr. Michael Behm. Okay, we go to the second session with Dr. Michael Behm from East Carolina University. Okay, with the Prof. Sorry, Prof. Michael Behm. Okay, sorry, Prof. Michael Behm. All right, so Prof. Will give a speech on the construction incident casualty. All right. So with us, actually, student, master student, I'm replaced Dr. Mazlina because of maternity leave. So without further ado, I pass to the Prof. Mike.
Sure. Thank you. Thank you so much. It's really a pleasure to be invited to speak to you all. I know it's the evening for you. It's the morning for me. So I'm having my cup of coffee in the morning. So I'll if it's okay, I'll go ahead and share my screen.
Yeah.
Is that okay?
Yeah.
Let's see if we can do this. Is it sharing? Okay. Is it sharing okay?
Yes.
Okay.
Yes, Prof.
Well, there we go. Yeah. So my name is Mike Behm. I'm gosh, I've been at East Carolina University. This is my 20th year at East Carolina University. So I'm a professor of occupational safety here. We have a Master of Science program in occupational safety that I lead and run. And actually for the last year, I've been so I'm in the engineering technology department, and but for the last year I've been an interim department chair of our construction management department. So I've been doing a little bit of a dual role and doing lots of different things. So, but one of the things I'd like to speak to you a little bit about is a little project that we a research project that we did here in North Carolina on construction incident causality. Well, I guess where am I? Where am I? So I think it's always good to kind of let people know kind of where East Carolina is. It's in the state of North Carolina. It's on the east coast of the U.S. It's I guess you could say we're kind of we're I guess between Atlanta, which is a pretty major city, and Washington, D.C., which is our capital. So we're kind of situated right there. So that's where I'm speaking to you from. And also please feel free to interrupt and ask questions. Let's treat this as a very interactive session. Again, it's my pleasure to speak to you all here today. Let's see if I can get rid of this. I wonder how, oh, there it goes. Okay, great. So accident causality, incident causality, right? Why do we investigate things, right? Why do we investigate accidents? Accidents are still fortunately, I think, are a pretty rare event when you think about the grand scheme of things. When you think about work on a construction site or on any site, accidents are still pretty rare. But when they happen, we say, "Oh my, why did that happen? Why?" And we really want to know why. And sometimes I think I'm going to challenge the group here. I've heard people say maybe we should stop investigating accidents. Maybe we should just study work and be more proactive because the accident already happened. And so I'm not sure I believe that quite yet, but it's an interesting concept to think about. But the questions you really have to ask yourself as an incident investigator is, does the past really predict the future? Because we want to learn from accidents and incidents. We really want to learn, not just to prevent that particular accident from happening in the future, but also to really learn about deficiencies within our system. And I think a lot of times that's where accident investigation falls short in practice. And we're going to talk about that. And then, boy, the last question on this slide. Are investigators biased? What do you think about that question? Are investigators biased? Anybody think they are?
Possible.
Very possible, yeah. We all have biases, don't we? We all have biases. So if you're in charge, if you're the supervisor doing the incident investigation, maybe somebody might say you didn't do a good job, right? Or you're a work crew leader, or a lot of times if you're the safety professional, you're like, well, I don't want to have any deficiencies come out that make me look bad, right? And so what happens? Well, we'll talk about what happens in those particular scenarios, right? We all see things differently. We all see things differently. It's all based on our perspective. And so as an investigator, we really need to be cognizant of our own particular biases and really go in from a learning standpoint. I really want to learn. I want to make the system better. And so understanding different perspectives when you're talking and interviewing people is really, really important. I like this particular picture. It gives a good explanation of things. So the ultimate question is, what causes accidents, right? What causes accidents? Have you ever heard of the term Wilfy whiff? You ever heard of that term, Wilfy whiff? What you look for is what you find, right? So that goes to the biases. This was a term coined, I forget. It was in a safety science article probably about 15 years ago, Wilfy whiff. And it really says, well, it's about the biases of the people who are doing the investigation, right? Many times we say, oh, it's the people, the person who got hurt, right? So we have those biases, and we'll look for all the things that person did or didn't do that influenced that accident, right? Other people take a very engineering approach, and they look at engineering and things of that nature, and they'll only focus on that. So what you look for it tends to be what you find, right? And then there's Whiffy whiff, all these acronyms. What you find is what you fix, right? So if you believe it's all about people and this word human error, which we'll talk about a little bit, then you're going to try to fix people. If it's about the system, you're going to try to fix the system. Well, so, I mean, if you read anything about accident causation and incident causation, gosh, there's so many approaches out there. It can be so confusing. And so, but there is these kind of two kind of approaches, this person approach and the systems approach, right? And so, I don't know. I kind of can't decide. So I think they're both right. And I think they both have value. And I think the truth kind of lies in the middle of those two approaches somewhere. There's value in all of it. And so I like to take what I think is a sensible balance of the person approach and the systems approach. And I'll show you a model that we used to try to get us to do that in a research project here in the States. And yeah, so this word called hindsight, right? There's always hindsight. That's another particular type of bias, specific to the investigation process, right? Because as an investigator, you have this great ability, maybe, to look back and say, oh, this is what happened. This is what the organization or the supervisor or the work crew or the person involved could have or should have done, right? So that's easy to say when we're doing that investigation. But in the moment, when things are happening in a very complex system, as work is, that hindsight bias is really something to keep in mind, because people don't think like that. You have time to think through what people should have done. In the moment, in real life, in real work, people don't necessarily always have the benefit of time. It's more impulse. It's happening. We have to react, right? So this hindsight bias that all investigators have, right? So, you know, Sidney Decker's done a lot of work in this particular area in terms of hindsight bias, a really interesting term. And so many of you have probably heard the term root cause, right? That's probably, oh, we need to find the root cause, right? Well, I don't know. I think that term can get us in trouble a little bit, and I'll talk about that. But I'd like to ask you, going back to maybe your biology courses, what kinds of roots are there in the plant world? Anybody know that question? What two basic types of roots are there? Well, that's a tough question.
Primary and secondary.
I'm sorry, secondary and
The primary and secondary root.
okay. Well, I'm thinking of the root systems in plants. And so the two basic types of root systems in plants are you know, this it's fibrous root A, and the tap root B. And so a lot of times when we say the word root cause, we're looking for one cause. When we say that, we're trying to pinpoint that one thing, that caused this accident. And many times we're focused on plant root system B, the tap root. And in fact, there's actually a consulting company here in the US called Taproot. And I am more of the belief of the fibrous root system representing accident causality. It's all over the place. It's complex. There's many roots. There's many roots that influence this plant and its growth and its structure. Just like there's many things that influence work and accidents and incidents. So I always, whenever I do a presentation on accident investigation, I always like to bring this out because you'll hear that term root cause, and almost everybody thinks find the one thing. And when they do that, the one thing usually ends up being the person who got hurt. They did or did not do something that caused that accident, right? And so we tend to focus then on that individual. And that maybe doesn't really present a really holistic picture of what really happened in incidents, right? So the problem I'll talk with you a little bit about today is the state of North Carolina, the Department of Transportation, and this study is, gosh, quite old now, probably 10, 12 years old now. But they had a problem, right? They're not doing investigations thoroughly enough to find what they claimed as root causes, right? So basically they were focusing on one thing, and that was on the people. And they realized they really can't change people. It's hard, right? So we're just all we're doing is blaming people for accidents, and they realize, well, this is a problem. So these are the folks, the Department of Transportation. You know, here, I'm not sure how it is in your part of the world, but these folks are out doing all kinds of things: building roadways, building bridges, repairing, maintaining, doing all kinds of stuff. Amazing what they get involved in. So lots of different things. So I'll talk to you a little bit about this particular research that we did. And there's some, you know, and I can get you these articles if you're interested. But it directly resulted into this particular manuscript. And I used this causation model called the Loughborough Construction Accident Causation Model, and I'll introduce that here today. And it was developed at Loughborough University in the UK. And at the same time I was doing my work, some folks in Australia were also using the same model, and I collaborate with Helen Lingard quite a bit, and she was using it, and of course the people at Loughborough were also using it. So we kind of were talking and said, hey, well, let's kind of look at how we all three of us use this model. So we produced this more of a macro type of a paper, and I can get that to you as well too. So this accident causation model, you know, starts with the accident, of course, in the middle, and it works its way out. And it uses terms like circumstances, factors, and influences. And I really like those terms. Those terms say a lot about that there's going to be multiple things happening along and through the system. And the idea of the model is that you're going to work your way back. And there's some details in here. And some of the details, they talk about those factors, right? So the immediate circumstances are the people, the work team, the workplace, the materials, and the equipment. And you work your way back through these various words and phrases to try to spark the investigator to think about how these constructs, these factors, these circumstances may have had an influence in the particular accident that you're investigating. And we'll talk about how we use that. And it goes on back, and it leads you back to what they call shaping factors. So things like, you know, work scheduling is going to influence the layout and space, the local hazards, right? And that's going to ultimately influence the accident. So these are a series of words and phrases to try to get you to think about things. So, oops, let me see, I think I'm going backwards. And it goes on back, you know, trying to look at what they call originating influences, which are really difficult to really try to identify, but things like the design of the permanent works, you know, how the project was overall managed. Safety culture is a word they used, and that's, you know, that's an interesting word. You could probably have a whole session or 3 or 4 on safety culture and what does that mean. But we did operationalize, we defined all these words and phrases so that we, as the research team, could use these words and phrases consistently throughout our investigation processes. So that was one thing that the words weren't very defined when we actually got this causation model from the folks in the UK. But the process, it's a very linear type of a process, kind of after James Reason's Swiss cheese theory, where the holes represent gaps, and the loss can happen. And so this is kind of the accident trajectory when you look at those 3 different things. And so it's a very linear type of a model. And that's okay. But you have to realize, right, that we kind of see things, A to B, right? But when we get out in the real world, yikes, things are a little bit messy in the real world, and it's chaotic, right? And so A doesn't always go to B, it's A to B to C, and there's Z in there somewhere, and it's chaotic, right? And so to really try to understand what happened retrospectively without being biased, to try to remove hindsight, wow, that's a really difficult job for an investigator and any accident investigation model. I'm not sure we really have a really good systems-based accident causation model. I think we're getting there slowly, but I'm not really sure the profession and safety science is really quite there yet. But this is my version of I really like this slide. I like this kind of version of when we're in the office, when we're behind our desk, things seems very, very simple, but in the real world, it's not simple at all. So we really have to keep that in the back of our mind, again, to reduce that bias that any investigator, that any safety professional is going to bring to the table. There's other things, right? And so there's other ways to model things, just showing you different types of things. This is FRAM, the functional resonance analysis method. You could learn more about that from Eric Holnagel. Mind mapping is a good way to kind of look at accidents and how things happened. We do this kind of stuff with our students. This is in Dutch right now, taken from a colleague. But we do with my students. We try to create mind maps and how things are happening in a positive and a negative way. But anyway, back to our Loughborough accident causation model, or what I call the Gibbs-Haslam model, because these are the 2 guys who came up with it. So I'll use that. So Gibbs-Haslam and the Loughborough accident causation model, they're the same thing. And so there's some principles that we developed through this particular research, right? So and that we tried to instill then in the North Carolina Department of Transportation, that there's always multiple causes. There's always, there's never a single cause. Very, very seldomly, if ever, is there a single cause, right? So those are some principles that go into this particular thinking. And our purpose is to find all causes, right? And so in working through this model, we treat all these phrases, there's I think 24, 22 phrases, right? You treat them as questions, right? So if it's about attitudes, actions, and behaviors, right? You turn that into a question. Did worker attitude or motivation influence their action and behavior? If so, how? And justify that. And we created a whole document spreadsheet to kind of put the, you can imagine an Excel spreadsheet where these are kind of in there as well too. And in addition, we go through and we highlight on the model to help us spark questions of the people that we're interviewing. And that's really important too, is to interview lots of people who have, so not just the work crew, not just the person who was hurt, but the supervisors, the managers, other folks within that sphere of influence. So so we treated our work, we took a lot of time because we were treating our work like a research project. In the real world, people don't have a lot of time sometimes to really delve into the details of an accident. And I think that's the one unfortunate thing that I'd like to impart upon you, is that if you really want to do a good job at accident investigation, you really need to put some time into it. You need to take a few hours, a full day. And we interviewed multiple people. I mean, it took us many interviews, going back, trying to recreate the scene, trying to understand what was happening, going through old reports. So it takes a lot of time to really do accident investigation correctly. And many times your organizations will rush you to get those things done. And if there's any yeses that you find through these questions, you follow them back to identify causes and influences. We highlight them using a highlighter on the model. We use our spreadsheet in our forms to document the different causes and influences and how they've been used and justified. We had to create operational definitions of all these phrases that were in the model. Those did not exist at the time that we were using them, so we had to create them, because that's important to use them consistently. And so I'll just give you one quick example here. An employee, one of the DOT employees, was using an auger, and it's important to kind of understand here. So it was a 10.2 inch, and I'm sorry, I'm using the English units here, but 10.2 inch diameter, so a pretty big auger to dig holes to put signposts in. And I'll show you some examples of these signposts, because they were planting trees and they didn't want the mowers at the side of the road to mow over these new trees. And so they were digging these holes and putting these signs in about every 100 feet along this long highway where they planted trees. And of course, it was the end of the day, right? Accidents always happened. See, they seem to always happen in the beginning of the day or the end of the day. So it was the end of the day, of course. And so this is just this is not the road, but this is an example, right? So this might be a small example of something that they might plant with, but I'll show you kind of what they were putting in. But this is, the side of the road where they might plant some trees. This is the type of auger that they might use to kind of dig and put these particular signs in. And these were the types of signs that they were putting in. So don't mow yet. Let it grow, right? So so they wanted to warn the people who are coming through and mowing the grass, here's where we're planting stuff. Please don't mow over this. So these were going every 100 feet. Well, lo and behold, the auger hit a rock, kind of came up, and if you're kind of looking at my video now, it came up and kind of hit the person in the face. The auger came up and hit the person in the face. The employee said that they were leaning on the auger. They said, "Oh, I know I shouldn't have done that. I shouldn't have done that." So, of course, they kind of blamed themselves. So the auger kind of pulled the employee, and they hit the switch, actually, which was good, they said, because it shut it off, or they said it could have been worse. So, this is the actual auger that they were using. And you can see the diameter here at the very bottom. You can see the diameter, and that's important to this story, is the large diameter of the auger that they were using. So what we found is that they really didn't need that large of a diameter of an auger. They really needed something not 10 inches, but more about 3 inches at the most. But they didn't have they didn't have that type of an auger blade. And they didn't order one. They said they didn't have time to order one, and they just went out with these larger blades and just did this job. And it actually ended up being more work for them because they were pulling out more dirt to only plant these really small small signposts. So that's an interesting thing that we learned, that they didn't have the right tool. And so, but what the DOT said in their investigation, they said, okay, we're going to get rid of all gas-powered augers. We're not going to use any gas-powered augers anymore. We're just going to eliminate that. So it'll never happen again. So then they said, we're going to use these manual type augers, right? So you can imagine how hard that might be to do that. If you're doing that, you're digging this, probably one every 20 or 30 minutes throughout the day, and you're, pounding it into the ground, and the ground can be hard. Boy, that could create some other hazards and risks, right? That could create some ergonomic hazards and risks to your shoulder, to your back. It's a lot more manual labor than these gas-powered augers. So we question, well, is this the best solution as well? And so this particular accident, we question a lot of different things. You can imagine about the equipment, the availability, the suitability of the equipment, and then in terms of trying to improve the system, right? So, it only would have taken a couple of days for them to get the new blade in. And so if they just would have had that new, smaller blade, maybe this accident wouldn't have happened. It would have been easier. They wouldn't have been bringing up so much dirt, and the option of hitting something would have been much less. So those are the types of things that we question, those types of system things within the accident. And so overall, we looked at, I think 27 accidents, and we found about 6 factors of influence per accident. And when the NCDOT, when they did theirs, they found usually one or two factors and influences per accident. Usually that was focused on the individual. It was focused on the person. And so, so we found a lot of things within the system. We thought that was good. We did find worker actions and behaviors, no doubt. But we didn't stop there. That's an important piece of that story, is that we didn't just stop at the worker actions and behaviors and say, oh, they should have done something differently, right? But that's a lot of times that's what the NCDOT, that's what they did, right? So we found lots of different things. We found local hazards quite a bit because they were getting involved in lots of different, all over the state, all kinds of terrains, right? And so the so what of this little research project in accident causality was that, if we can identify these kind of multiple influences beyond the obvious, right? Beyond the employee should have done something differently, right? Hopefully, the North Carolina Department of Transportation are able to more effectively and be more proactive about identifying different system type trends and multi-level trends, so that they can create more proactive and preventative programs in the future. And so I'll just kind of try to wrap things up here a little bit in the next 5 or so minutes. And so, they definitely were looking at the employee, and a famous quote by James Reason. Hopefully you've heard of James Reason, great organizational psychologist who has done a lot of work for safety science in the 80s and 90s. I think there's a great quote. We cannot change the human condition, but we can change the conditions under which humans work. And that really goes to the system, right? That goes to planning. It goes to being proactive. It goes to prevention, right? Professor Nancy Levinson has also done a lot of work in the world of system safety, and you know, the North Carolina DOT used the word human error quite a bit in their investigations. Human error, right? And so we need to remember that human error is a system that needs to be redesigned and planned better and organized better and communicated more efficiently so that we can be really proactive, right? And so that kind of goes to my first challenge. You know, should we even investigate accidents? What do we learn from them, right? The DOT wasn't really learning anything from their incident investigation. I hope they are now. I hope they're learning and looking within the system and trying to be more proactive, and turning what they learn into preventive measures. But is your organization really learning from accidents and incidents? Or is it really, is it a waste of time? It's a very challenging question for people to really kind of take a look at. So I think my final thoughts for you are that accident causality, you know, it is complex. It is that picture that I showed you, because work is complex. Life is pretty complex when we look at things, right? And there's always never a single, oh, that should be root, not rot. Root cause. There's almost never a single root cause, right? And know your biases, right? So if you're working for an organization, right, you bring your own biases to the table. When you do an accident investigation, we had the benefit of, you know, as a research team, as an external third-party research team, we had the benefit of, you know, we're not accountable to them per se, in terms of our job is on the line, or someone's going to come back and say, oh, well, you're finding things that you should have been doing, or you're blaming, you know. And the other thing we don't want to do, we don't want to blame supervisors, right? So a lot of people think, oh, well, if we're not going to blame the worker, then we should blame the supervisor. Well, that's not a good answer either in things. So know these biases and know everybody else's biases. That's really important as well too, because whenever there's an accident, a natural tendency by most people is something, this terrible 5-letter word called blame, right? And sometimes, you know, and blame and accountability are two different things. So that's a whole other probably session or two on blame and accountability, but everybody has these biases. And so I really encourage you to go beyond those immediate causes and go into the system of work. And I'd be happy to take questions or comments about, you know, what we talked about here today. I'd be happy to share the presentation as well with the group.
Hello, Professor Mike Behm. I am Farid. I have a question.
Yes.
Usually during investigation process, the person or subject will be defensive. So what if there any false information during the investigation using the Gibbs-Hasler model? Does it affect the result, or are there any other factor or indicator to deal with the situation?
Wow, that's a really good question, Fareed. Thank you for that. I think that goes to the biases within the organization as well too. I think you know, the answer really is, it depends again on a lot of different factors. So if you're an internal investigator, internal to that organization, and there's not a lot of trust within the organization, I think you're going to get people who are defensive because they've seen their peers maybe get blamed for things that maybe they thought were not justified. So that's going to lead to that being defensive, right? And so, that's those biases. And so if you're in that type of an organization, right, trust takes a long time to build, but we have to start somewhere. And, I think if you go about it, more of there's a really good book called Humble Inquiry by Edgar Schein. And it's a lot about asking humble questions, right? Without a lot of times the investigator might think they know what's happening. And so that's also that bias, right? And so we need to be more humble inquirers. But you ask it's a great question. I'm not sure I gave a good answer there. I'm not sure I gave an answer that you could just kind of take and say, okay, well, that's the answer. It's a complex question. It's a great question. I love when people ask. I love when people ask questions that are really challenging, and so that's a great question. Thank you.
Thank you, Doctor. Because it's deal with the human behavior, right? It's so complex.
Yes, humans are complex. We are very complex. Thank you. It's a great question. Great comment.
Thank you, Doctor.
Good morning, Dr. Matter. I have a question. Just to talk about personal bias. So many professions in the United States are individual practitioners, and the personal bias will inevitable not appear in the work. If an accident occurs in the field of individual practitioners, cause casualties, how can investigators put aside their bias to investigate these individual practitioners? So who cause accidents due to bias because people can't avoid their own bias?
So
Doctor?
you're more speaking about you're almost investigating the things that you should have done as the safety professional.
Yes, such as personal practitioners, such as engineers, architects, or doctor, or some constructors. This individual can personally register their occupation as different to our country, China. So I want to know if this individual cause accident or some casualties according to her bias. So, and let's some inspector who I want to see how can investigators put aside their bias to investigate these individual practitioners?
Yeah, that's again, really great question. I think, I'm not sure how it is in your part of the world, but it depends on who does that investigation. And so if it's an external governmental person coming in to do the investigation, there's a lot of people don't want to talk, right? People don't want to talk about things. Your organization is going to be very quiet. So that's it sounds like it looks like from the smiles around the room, that's how it happens in your own, kind of parts of the world. It's all kind of the same. But as soon as that governmental person comes in, boy, we get quiet, don't we? But in terms of being that internal investigator, you know, that's, you know, you really need your top management support that, you know, they're going to say, we really want to know how we, and, you know, and it's more, it's a plural, how the organization, if we think about more the organization more so than individuals, I think your biases are reduced. And so rather than trying to point a finger at an individual, you look at the organization as a whole, and it's a more of a collective. We should be doing these things, whatever they are, better to prevent. We should be doing these things more proactively. We should be making these particular changes, right? And so, you know, that I hope that answers your question, you know, kind of both externally and internally. But that's a really, again, that's a good question. Really good points. Thank you.
Thank you, Doctor. My question is cute. I want to say sorry because as just according to some political issues, as different some differentiate some country. Finally, thank you, Doctor.
Thank you for your question. Thank you. Great points.
Hi, Prof.
Hello.
My name Anwar. I would like to ask whether you have the real experience regarding this issue, which government interfere with the investigation in any accident.
I worked, so before I became an academic, I worked for a large multinational corporation, and I was, you know, the more in the North American corporate office, and gosh, we had about 100 facilities, manufacturing facilities and quarries, mining quarries. And during my 7 years there, there was a couple fatalities, and I was involved in one of those. And you know, being the corporate person, I wanted to, you know, I became that kind of liaison between the government officials and the local plant officials. Ooh, that was a that was a difficult situation as well too, because I have an ethical and moral responsibility to ensure that I'm telling the truth, right? And so sometimes the local facility did not want me to say the truth all the time. And so that really put me in a very, very difficult bind. And fortunately, you know, the corporate office supported me in telling the truth. And so, you know, I think you're going to get that as well too. When you get an external investigator, you're going to have people internally saying, you know, well, you know, maybe you should take a couple weeks off and not come in or something, or you should, you know, I mean, that might be your best bet, is to take vacation. I'm being silly now, but yeah, so I did have that experience, and that's very uncomfortable, very uncomfortable. And if you don't have your management support to help that investigation go forward in a truthful, honest way, then you're going to be very uncomfortable.
Thank you for that. Sure.
No,
Is it
really good questions. Thank you.
is it because of that you changed your path to academic?
No, that's a really good question too. No. Gosh, you know, I think anytime, you know, I was just curious. I was curious about a lot of things, and yeah, that's a really good question.
But in your attempt, our colleague because of that, we change to the condition.
I have similar experience regarding this issue.
Yeah.
mhm,
So what's happened that I told them that I'm going to make a police report if
mm.
they try to hide this thing. Then only after that everything is follow the procedure properly. But for the moral issue, they did something that is not very comfortable for me.
Mhm.
We managed to do it proper way actually.
Good, good. Yeah, it's I think when we as safety and health professionals, when you're no matter what industry you're in, it's always you always get into those kind of contentious situations, and you want to be able to speak the truth, and you want to hold to those codes of ethics that your profession subscribes to, and those are important things. Yeah, no, I well, and I've been in so many other situations outside of accident investigation as well too, just trying to when some of our facilities wanted to hide accidents and not report accidents and things like that. um, those are also you you need a good boss. You need a good supervisor and a good manager to support you.
Okay. Any other thought, Anderson? Do you have any question? No? Dana? No. Any other question, Esther? No.
It was so nice to be able to speak with you all today, and really
Yeah.
great questions. Wow, really, really good points.
Because most of them are working, so we are always sharing our experience.
Yeah, I think that's great that you do this because we kind of run things the same way
Mm.
as well too, and it's the experience of all of the collective group of students that really adds so much value. All the different experiences and views, and trying to centralize them into one cohesive hour is is always challenging, but it's fun. It's fun.
All right. Okay. No more question for this? All right. I think it's thank you very much for Prof Mike for your experience, your knowledge, and sharing with us. Okay. I think that's all for today. But okay, before we end our session with Prof Mike, we take a snap of picture first. All right, ready, guys? Okay, 1, 2, 3. All right. Okay, thank you very much, Prof.
Thank you so much. I hope you all have a great day. Best
Yeah.
wishes.
Thank you,
Thank you,
Doctor.
Prof. Mike.
Thank you, Prof.
Thank you,
Nice
Dr.
share.
Mike.
Just wait dulu ya. Okay, dah.
Dah, dia dah keluar.
All right. Okay, guys. Thank you very much for your commitment. Okay. All right. So, just make it short. Today is our last class. Okay, before you are going for the final test.
Next week.
So your final test on Friday at 8 o'clock. Okay, until 11. So three hours. So good luck. Okay, so your assignment and project presentation is done. Okay. Another pending task. Your
Doctor.
project and report for site visit, right?
Yeah.
Yeah.
Only
Doctor,
yes.
regarding our concern with the
Submission for the beneficiary.
yes, Doctor.
All right.
I- the one that we submitted is pixelated. That's our concern. Is it okay already?
I need to check with Dr. Lina first. Then I will come back to you. In case we are not received, you just email. It's okay.
Yes, yes, Doctor. We emailed already.
Yeah, alright, I receive. Okay.
Doktor, apa
Yes.
ni, kita pun dah email tapi kita tak CC Dr. Lina sebab at first hari tu
Itu
masa
report
BB
highlight, right?
report highlight.
Because our report highlight, Dr. Lina will marking. So it's okay. You just email me balik lah. Because I will handle on the presentation only, and then your final test I will marking. So Dr. Lina will marking on your assignment.
Doktor, so
Macam mana ni?
kalau kita just forward email to Dr. Lina boleh?
Boleh je.
Sebab
in case dekat view future tak dapat.
sebab bukan memang you future tak boleh
Tak
nak
boleh.
upload dah sekarang.
It's okay. Tak apa. You I think you email balik and then CC to Dr. Lina. Sebab Dr. Lina akan marking.
Hari tu masa BB tanya dia tak time tu tak ter-CC yang saya tak ter-CC dia sebab ingatkan macam doktor je. So
sebab
memang tak ada CC.
Dr. Lina yang ajar kan. So siapa yang ajar dia yang marking. Dia macam tu. Sebab tak nak nanti ada different thought kan. So nanti I punya pendapat lain. Tak macam tu. Okay. Tak apa.
Pujuk, pergi pujuk. Anwar pergi pujuk.
Tahulah, kami berharapkan Cik Anwar dia sekarang ni. Macam mana ni? Sebab doktor kita bukan tak submit. Kita dah submit tapi masa tu tak boleh upload dan kita letak link Canva je which is macam I believe that doktor semua boleh tengok pun dekat Canva tu.
Sebab dia kalau boleh nak terus download lah. Senang sikit. And then yang group yang last present tu siapa? Group Esther. Because ada kat YouFuture only PDF. Submit PowerPoint sekali.
Tapi dia suruh kita upload juga YouFuture tu macam mana? Takkan nak pergi berbahas dengan dia.
You buat dua-dua.
Dah, I try contact Iki lah malam ni. Tapi tak tahulah dia respon macam mana. Sebab kalau dia respon come back to the Dr. Lina, nanti Dr. Lina akan macam
Cakap je lah, memang technical. Memang tak boleh nak submit dah kan.
Dia tak ada yang tekan upload
dah
tu
tak
tau.
boleh
Dia tak
sebab
tekan
dah tak ada upload.
Even kalau
Kalau try semua tu tak boleh juga
pun tak boleh
Tak boleh.
Tak boleh.
kecuali ada button reject submission tu, then kena resubmit balik dan okay kot.
Dia tak
Tapi
boleh reset Encik Anwar.
Button dekat mana you submit ni? Sebab I tak tengok akaun Dr. Lina.
Yelah
You
kalau
future.
yang you future tu.
In case lah, I boleh tengok dekat dia punya. Sekejap Bahagian what? Assignment ke?
Cuba Anwar share yang bahagian yang tak boleh tu. Boleh?
Sekejap, I share my screen. In case lah. Macam mana nak share my screen? Sekejap. I nak share the full screen. This one ke?
Ketua kelas.
Pandai je.
Okay, you all nampak tak I punya screen?
On the way. Okay, nampak?
Okay, so dekat mana you submit? Continuous assessment?
Yes.
Or assignment?
Continuous assessment.
Assignment.
Group.
Mana? Group presentation ke?
Bukan.
I think
Sepatutnya dekat situ ada 3.
Tu BB tu.
Sini.
Tu submitted.
Kenapa late submission?
Tapi ni group submission.
I think this one ni presentation.
Ini bukan yang high rank ni, yang the first one hari tu. Dia sepatutnya ada satu lagi.
Bukan ni.
Baik. Bawah.
Doktor, supposedly
kat luar.
assessment tadi tu ada 3.
Sepatutnya ada 3.
No, dekat assignment tu ada 3 task. Group presentation, high rec dengan site visit report.
Betul.
Tiga-tiga appear dalam kita orang punya. So far tadi high rec Dr. Lina dah update dia punya due date sampai 30 hari bulan. Yang saya dapat tengok.
I see. Itulah, rasa my view only dapat group presentation je. Sebab Dr. Lina tak masukkan saya ke? I don't know.
Mungkin sebab doktor dia bagi doktor ni, sebab yang ni doktor boleh sign yang akan check bagi mark kan. Dia allow doktor untuk benda ni kot.
Yes, itulah. So you kena tengok Dr. Lina.
Ni saya tunjuk yang kita orang punya.
Okay, how?
Uh,
I stop. Sebab yang ini je my screen, bukan tak nak tolong. Tapi
Okay.
alright.
So ni
Continuous assessment.
sama.
Continuous assessment assignment.
Okay, ni
Ada.
group high rank kan.
Yes.
Lepas tu,
So bila
Submit.
kita submit,
Aha.
nampak tak ada attachment apa-apa. Tak boleh nak tekan apa-apa dah.
Oh,
Attachment tak boleh. Tengok ada back je. So tak anything tak boleh nak ni apa-apa.
I see. Kejap-kejap I ambil gambar. Alah, saya tunjuk kat Dr. Lina. Kat you all ni. Okay. So I boleh bagi tahu lah just technical issue.
Alamak, kejap.
Siapa yang mesej saya ni nak keluar, minta keluar awal nak Abu Zulaika. Okay. Tak dia cakap pasal apa arrange towing kan kereta I kena towing. Kejap
That's also our concern, Doctor. The one that we attach is
Okay, so okay.
pixelated.
Tomorrow I inform Dr. Lina. Don't worry. Okay. I lupa lah nak stop record.